Good morning everyone. I Aditya from BSC Chemistry Honors second year is today here to explain the chapter Lanthanide and Actinides in my presentation. I am from BSC Chemistry Honors second year. Let's start with the introduction. The lanthanides and actinides are the groups of elements in the periodic table. They are the elements that are often listed below in the main section of the periodic table. There are 30 total elements in the lanthanides and actinides. Therefore, they are also known as inner transition metals because their properties are lying between the metals and the non-metals. Let's start. What are lanthanides? The lanthanides are the elements with the atomic number 57 to 71. These 15 metals, along with the scandium and yttrium, are often called the earth rare metals because they are found in very tracer amounts. They are all silvery white metals which are often found in the same ores. They are called lanthanides because they exhibit similar property to the lanthanum, the first element in the group. What are actinides? The actinides are also the 15 elements with atomic number ranging from 89 to 103. They are named first in the series actinium. The actinides group include mostly man-made metals with only a few exceptions such as urium and thorium. The actinides are most known for the elements uranium and plutonium which are used in nuclear reactors and nuclear bombs. Let's see their position in the placement of periodic table. If we put lanthanides and actinides into the periodic table like transition metals, the table will be too wide. To shorten the tables, the two rows of elements present at the bottom of the periodic table are called 4F series of lanthanoids and 5F of actinoids. They are also called inner transition metals because they are placed below the periodic table. As you see in the figure, the lanthanum in atomic number 57 and the last is with the symbol Lu71. They are called actinides. They are seen in the violet boundary. Below that we see actinium atomic ranging the atomic number in 89 and to the last we see the 103. These are present in brown color. Hence, their position is below the periodic table because they are not put in the periodic table so that if we put them, the table becomes so wide. Now, let's see the electronic configuration of the lanthanides. Let's take an example to understand the electronic configuration. Let's take lanthanum with symbol La and atomic number 57. Its configuration in ground state is xenon 6s2 5d1 and in the Ln2 plus state its configuration becomes xenon 5d1 and in 3 plus it becomes xenon 4f0. Its radius is 188 picometer and in the 3 plus state it is 116 picometer. Now let's take another example from the series. We take the example of lutetium, the last element of the lanthanides. Its symbol is Nu with the atomic number 71. Its configuration is xenon 4f14 6s2 5d1. In the state Ln2 plus its configuration will become xenon 4f14 5d1 and in the 3 plus states in configuration becomes xenon 4f14. These all the configuration are in the increasing order of the F subshell and its radius is 173 picometer and in the 3 plus states its radius is 98 picometer. As we see the radius is decreasing as we move below the series. Now let's see the oxidation state of the lanthanides and actinides. The common oxidation state shown by all the lanthanides is +3. Some elements also displays the +2 and +4 oxidation state, but these are always less stable than the group valency of +3. The unusual oxidation states touches +2 and +4 exhibited by the lanthanides and can be explained on the basis of the extra stability associated with the empty half-filled and fully filled 4f subshell. Oxidation state are the number of electrons that a atom consider in its outermost shell. Let's see, U and YB exhibit the +2 oxidation state because in this +2 oxidation state, europium with symbol Eu and ytterbium with the symbol YB acquire F7 and F14 electronic configuration. This is because the F7 and F14 are provided the extra stability due to half filled and fully filled orbitals respectively. In the europium 2 plus states, its configuration will become xenon for F7 and in of ytterbium its configuration becomes xenon for F14. Due to this reason, they exhibit the +2 oxidation state because they will acquire the extra stability in the +2 oxidation state. Let's take the example of cerium and terbium. They exhibit the +4 oxidation state because in the +4 oxidation state, cerium and terbium acquire F0 and F7 configuration, which are supposed to be the very stable configuration because F0 have the zero filled orbitals due to which they will acquire the extra stability. Let's see the configuration of cerium and terbium in +4 oxidation state. Of cerium, the +4 oxidation state, its configuration is xenon 4f0 and of terbium it is xenon 4f7. Here in this the F subshell is half filled, which will acquire the extra stability than other one. Now see the electronic configuration of actinides. For understanding the electronic configuration of actinides, let's take an example from all the elements. Let's take example of actinium with symbol AC and atomic number 89. Its electronic configuration in the ground state is radon 6d1 and 7s2, and in the 3 plus states its configuration will become radon 5f0. Also, the radius of the M3 plus of actinium is 111 picometer and of 4 plus it is 99 picometer. Now let's take another example of thorium. Its symbol is TH and its atomic number is 90. Its configuration is in the order radon 6d to 7s2 and its configuration in 3 plus state is radon 5f1 and in the 4 plus state it's become 5f0. Hence its radius in +4 state is 94 picometer. Now let's take another example from the series of lawrencium, the last element of the actinides with symbol Lr and atomic number 103. Its configuration is radon 5f14, 7s2 and 6d1. And in the 3 plus states its configuration is radon 5f14 and in 4 plus state it is radon 5f13. As you see in the figures, the electronic configuration are filled according to the increasing order of their F subshell. As we see in the protactium it is 5f1 and in the lawrencium it is 5f13. It is filled in the increasing order of their electrons. Now let's see oxidation states of actinium. As I already told, the oxidation states are the number of the electrons in their outermost shell. As we see, the actinium possesses +3, thorium possesses +4 and uranium possesses +3 to +6 all the oxidation state, and likewise other elements also possesses some oxidation state. It is found that the most stable oxidation state of the elements up to the uranium involving all the valence electrons. Neptunium forms +7 oxidation state using all the valence electrons, but this is oxidizing and their most stable oxidation state of the neptunium is +5. Plutonium also shows that the states up to +7 and americium up to +6. But the most stable oxidation state drops to plutonium of +4 and americium of 3+, and the later elements tend to be stable in plus 3 oxidation state. The berkelium in plus 4 oxidation state is stronger oxidizing but is more stable than the curium and americium in the plus 4 state due to the F7 and extra stable configuration. Similarly, the nobelium is marked stable in the plus 2 oxidation state due to its F14 configuration as its all the subshell are fully filled by the electrons. Now see the term symbols. Each energy level of an atom is described by not only by its configuration but also its term symbol. The word term refers to the energy level, so a term symbol represents a electronic state of a particular type of atom. The ground state's term symbol is 2s plus 1 Lg. Separation and synthesis. Now see the synthesis also and the separation of the lanthanides and actinides. Firstly, see of actinides that bastnasite and monazite are the main source of the lanthanides. Monazite is the mixed phosphate with the empirical formula LnPO4, and the bastnasite LnCO3F is the source of the lighter actinides. Techniques for separation. We can use precipitation, complex formation, solvent extraction, valency change and ion exchange for their separation. Now see the chemical properties of the lanthanides. Metals of plus 3 oxidation state are electropositive. Also the sum of 3 ionization energy is minimum for lanthanum, Gd3 plus and lutetium plus 3 oxidation state. The standard reduction potential of the elements is very high. Basicity decreases as ionic radii decreases from lanthanum to lutetium and from actinium to lawrencium. Metal react with the hydrogen to form the hydrides, and these hydrides are decomposed by the water and react with the oxygen. Let's take an example of cerium hydrides react with water to form cerium oxide and the 2 moles of hydrogen gas. Also, the anhydrous halides with the empirical formula Mx plus 3 from metal and halogen react in the order Ln to O3 plus 6 mole of ammonium chloride at the temperature of 300 degrees Celsius forms LnCl3 and 6 mole of ammonia plus 3 moles of water. Also now the 3 mole LnCl3 with 6 mole of water when heated will form LnOCl plus 5 moles of water and 2 moles of HCl. The hydrides of actinium. Uranium reacts with hydrogen at room temperature to give the hydrides. U plus the hydrogen gas will give UH3. That means uranium trihydride. The trihydride will react with 4 molecules of water to form the uranium oxide and 7 moles of the hydrogen. Uranium hydrides with the HCl will form uranium chloride with 3 moles of hydrogen. Oxides. UO2 with the black color and U3OID with the green black and UO3 with the orange yellow color. These are the colors of the oxides of the uranium. Now let's study something about uranium. Uranium exhibit plus 3 to plus 6 oxidation state. Most of the compounds are formed by the taking uranium oxide. Uranium hexafluoride is colorless volatile liquid. Uranium hexafluoride is vigorous fluorinating agent. Also when react with barium boron chloride, it will form uranium chloride that is unstable. Uranium fluoride will react with water to form UF4 and 2 moles of hydrogen fluoride. UF4 is inert, sparingly soluble and green color gas. Oxides. The UO2 is in black color whereas U3O is green black and UO3 is orange yellow as we have already studied earlier. Now let's see some another reactions. UO2 with 2 moles of NO3.2H2O reacts at very high temperature to form the uranium trioxide and then react with 350 degrees Celsius with carbon monoxide to reduce to uranium dioxide. Uranium trioxide at very high temperature, that is 700 degrees Celsius, will form the triuranium oxide. All the oxides are basic and dissolved in the acids. Some reactions of fluoride are when uranium dioxide reacts with hydrogen fluoride will become uranium uranium tetrafluoride, and when it reacts with the hydrogen bromide at the temperature of 65 degrees Celsius it will form the uranium hexafluoride. Also, when uranium tetrafluoride reacts with the fluorine gas at a temperature of 240 degrees Celsius it will become uranium pentafluoride, and when it reacts with the hexafluoride it will form the UF6. It means uranium hexafluoride with negative charge and uranium octafluoride with the negative charge. Uranium hexafluoride and uranium hexachloride are octahedral, but all other halides are polymeric and have the higher coordination number. UF6 obtained from the classless crystals and a powerful fluorinating agents. Americium dioxide with 2 plus charge is a strong oxidizing agent just like potassium permanganate with the formula KMnO4. Coordination complexes. Since F electrons are buried, ligands are placed with minimal interligand repulsion. The lanthanum 3 plus being large hard Lewis acid adopted with higher coordination number. The high coordination number of LnH2n with the formula N having the 3 plus positive charge is equal to 9 for early lanthanides and 8 for the later one. Whereas YB ytterbium forms 7 coordination number complex with the formula YbAcAc thrice H2O, and large lanthanum 3 plus forms 8 coordination complex with the formula LaAcAc thrice H2O twice. Its structures are shown in the figure with the coordinating ligands having LnF3 and YbAcAc thrice OH2. Here we see the structures of the following coordination complexes. These structures are obtained by the X-ray diffraction. Now let's see the spectroscopic properties and color. The trivalent ions are strongly colored. Color depends on the unpaired electrons. The cerium and terbium are colorless and pale yellow respectively due to the strong absorption of the 4F5D transition. The F0, F7 and F14 ions are colorless because in these the configuration is empty, half-filled and fully filled respectively. Spin-orbit coupling is more important than the crystal field splitting according to Russell-Sonder coupling. Absorption due to FF transition are sharp and 4F and 5D are broad in lanthanides. The exception is lutetium with 3 plus positive charge. The colors of the complexes of lanthanum and Ln3 plus are observed and calculated the magnetic moments of the M3 plus ions. As we see, the lanthanum with 3 plus positive charge are colorless, cerium also colorless, and we see that the terbium with 3 plus positive charge have the pale pink color. As we also already see the ground state electronic configuration above, also the calculated magnetic moment and observed magnetic moment have very little difference as we can see. Let's take example of terbium to see the magnetic moment is 9.72 calculated and it is observed is 9.4 to 9.6. Luminescence of lanthanide complex. Irradiation with UV light causes fluorescence in the Ln3 plus complex. However, in some cases very low temperature is required to observe this. Origin of fluorescence for F4F transition, no transition being possible for F0, F7 and F14 complex. Example, let's take example of europium 3 plus having the red emission, whereas the terbium with 3 plus positive charge having the green emission. They are useful commercially for obtaining some products or some device in the use of some devices. Lanthanoid metals. Lanthanum and lanthanoids crystallize in one or both cubic or HCP lattice except europium. EU that is europium crystallize in BCC. Magnetic properties. All the lanthanides with the exception of lanthanum, lutetium and ytterbium and cerium 4 plus are paramagnetic because they contain unpaired electrons in the 4f orbitals. Its magnetic moment be calculated as under root 4 s plus 1 and l plus 1, where the s is equal to spin quantum number and l is equal to orbital quantum number. In lanthanides and actinides, the spin and orbital contribution couples, which gives a new number J, whereas the magnetic moment now calculated by the G under root J plus 1, whereas G is equal to 1 plus 2J plus 1 S plus 1 minus L plus 1 plus J bracket J plus 1. In actinides, J is twice than that of lanthanides. Magnetic properties are same as lanthanides of actinides. Applications of lanthanides, metals and alloys. The pure metals of lanthanides have very little use. However, the alloy of the metals can be very useful. For example, the alloys of cerium has been used for the metallurgical applications due to their strong reducing abilities. Non-nuclear. The lanthanides can also be used for the ceramic purposes. The almost glass-like covering of a ceramic dish can be created with the lanthanides. Nuclear. Like the actinides, the lanthanides can be used for the nuclear purposes. The hydrides can be used as the hydrogen modern carriers. The oxides can be used as diluents in the nuclear fields. The metals, for being good as structural components, they can also be used for structural alloy modifying components of reactors. In life science, it is also possible for some elements such as thulium can be used as portable X-ray sources. Other elements such as europium can be used as radiation sources for the treatment of cancer. Lanthanides as MRI contrast agents. The MRI is generated by the information obtained from the 1H NMR spectroscopic signals of water. The signal intensity depends upon the proton relaxation time and the concentration of water. The relaxation time can be altered, that means changed, and the image can be enhanced by using the MRI contrast reagents. The coordination complexes containing the paramagnetic GD, Fe3 plus or Mn2 plus are potentially suitable as contrast agents, and of these complexes containing the GD3 plus ion has so far proved to be especially useful. As a free ion, GD3 plus is extremely toxic, and therefore to minimize the side effect in patients, GD must be introduced in the form of a complex that will not dissociate in the body. Example: JD DDPA OH22 minus by the magnetist was approved in 1988 for the medical use as an MRI contrast reagent. The second one is by the Omniscan and third one is by Prohance. These three are classed as under extracellular contrast agents. Once injected, they are distributed non-specifically throughout the cellular fluids. Elimination and easy through the kidney with the half-life of around 90 minutes. The structures of the complexes are shown. Now, lanthanides and NMR shift agents. The magnetic field experienced by a proton is very different from that of the applied when a paramagnetic metal center is present. This results in the large range over the 1H NMR spectroscopic signals appearing being larger than in the spectrum of related dimagnetic complex. The signals for the protons close for the paramagnetic material center and are significantly shifted, and this has the effect of spreading out the spectrum. Generally, low and midfield NMR instruments are daily used for the research, and in this case, paramagnetic NMR shift agents may be used to disperse the overlapping signals. Allen complexes are routinely employed as the NMR shift agents. The addition of the small amount of a shift reagent to a solution of an organic compound can lead to the equilibrium being established between the free and coordinating organic species. The result is that signals due to organic species which originally overlapped spread out and the spectrum become easier to interpret or study. The uranium in 3 oxidation state complex is shown below is a commercially available shift reagent having the structure as shown. The color code is La is green, N is blue, red is C, grey is H, white X-ray diffraction data by the GM Harrowfield at the Australia J Chem laboratory. Thank you.